Hello, welcome to Chapter 9, where we're going to be looking at solutions. We've already briefly been talking about solutions. We discussed the idea of aqueous solutions when we were writing balanced chemical equations, and now we're going to really take a look at what that means. And this is going to be especially important for us because so much of what you're going to be looking at, especially those of you going into healthcare and health sciences, are going to be different chemical reactions that are occurring in the body. And in the body, we know that majority of our bodies are made up of water. So we really need to understand what's happening here. But of course, this is a chemistry class, so we're going to look at it from both sides. We're going to look at it from the healthcare side, and we're going to look at it from the chemistry terminology. And so speaking of terminology, we need to look at a couple of keywords before we fully get started. And so we have here what it means to be a solution, and a solution is made up of a solute and a solvent. So let's start off by talking about what is a solution. A solution, you might recall way back from chapter 1, I believe it was, is a homogeneous solution. Now let's remember, what does it mean to be a homogeneous solution? Homo means same. So a homogeneous solution is one that looks uniform throughout. You cannot tell apart the different pieces that make up the solution. But since it is a mixture, we know that it's made up of several parts. And the two parts that make up a solution are the solute and the solvent. The solute is what is being dissolved. Now, most of the time, the solute is in lesser amount than the solvent. So we can usually kind of figure out what is the solute and what is the solvent based on that ideology, which in turn means that the solvent is what the solute is being dissolved in. So for us, as I mentioned before, most of what we're going to be doing and what you're going to be doing in your careers are dealing with water solutions. And so for being an aqueous solution, that means that we are in water, right? That was the definition of what it meant to be aqueous. So for all of our particular topics that we're going to be looking at, our solvent is always going to be water for an aqueous solution. So keep that in mind as we work our way through the remainder of the chapter, and this will even carry on into chapter 10 as well. So when we're dealing with our aqueous solutions, our solvent will be water. So now that we understand that a solution is made up by dissolving a solute into a solvent, we can understand this idea of solubility. And we've looked at solubility a little bit in lab in regards to precipitation reactions, but the definition of solubility is the amount of solute that will dissolve in a specific solvent at a given temperature. Now, what does that exactly mean? Well, at any given temperature, specific to the solute and the solvent, we will end up with a certain amount that can be dissolved. For instance, we can look at how much sugar will dissolve in water at 25 degrees Celsius. That's going to be a different amount than how much sodium chloride we can dissolve in water at 30 degrees Celsius. So anytime we're looking at solubility, we have to pay attention to the solute, the solvent, and the temperature. But there's a way for us to predict if something will be soluble in something else. And we use the rule that says like dissolves like. What that means is that a polar solvent will dissolve a polar solute. Likewise, a nonpolar solvent will dissolve a nonpolar solute. So we can kind of rewrite this as saying that polar solutes are soluble in polar solvents. And again, we can say the same thing for nonpolar. Nonpolar solutes are soluble in nonpolar solvents. So like dissolves like just means that if you look at the intermolecular forces or the molecular polarity of the two compounds, the solute and the solvent, if they match, they're likely to be soluble. So soluble means that it will dissolve. Insoluble means that it will not dissolve. So let me put that again in writing. Soluble means it will dissolve. Insoluble means it will not dissolve. So that's the common terminology that we'll use. However, that's specifically the terminology that's often used with solids. We use different terminology for liquids. So when two liquids will mix together, we say that they are miscible. This is called miscibility instead of solubility. So this is when liquids will dissolve in each other. And if they do not dissolve, we call them immiscible. So again, soluble and insoluble are often used with solids. Miscibility is usually used with liquids. So for instance, putting salt into water, we would say that is either soluble or insoluble. Pouring oil into water, we would say is either miscible or immiscible. But these all mean the same thing, like dissolves like, it's just soluble versus miscible tells us if the solute is a solid or a liquid. Now, how can we determine, besides just looking at the polarity of a substance, how soluble it will be? What we can also do is take a look at the temperature for solids versus gases going into solution. So solids, we see that the solubility increases as temperature increases. And let's think this through. If you have a cup of iced tea or iced coffee, and you have a cup of hot tea or hot coffee, and you put sugar into both of them, you see that with the hot substance, you just have to give it a little stir and that sugar dissolves right in. But for an iced tea or an iced coffee, you put in that sugar and you're just stirring for a long time. That sugar doesn't dissolve readily like it does in the hot beverage. Let's take a look at gases. So gases can also be soluble in different solvents. We say that with different carbonated beverages, right? We are dissolving carbon dioxide into an aqueous solution. So for gases, we see that solubility actually decreases as the temperature increases. And again, we can think about a bottle of soda. If you've already opened the bottle of soda, you drank half of it, you want to save the rest, what do you normally do with it? Most of the time, if you're able to, you're going to put it in a fridge. Because when we keep it at that colder temperature, the carbon dioxide is more likely to stay in the liquid. If we leave it out in a warmer temperature or room temperature, we know that the drink often goes flat faster. So solubility does depend on temperature, and it depends on the type of solute that you have, whether it's a solid or a gas. So now that we understand a little bit about solubility, let's take a look at how much solid we might be able to put into any given substance, any given solvent at a certain temperature. And we're going to do that by looking at the idea of saturation. But before we look at saturation, we need to talk about the idea that ionic compounds do something a little bit different than just dissolving. Dissolving just means that it becomes aqueous. So sugar can go from its solid form to its aqueous form, but other than changing the state, nothing really happens to it. But recall that ionic compounds are in lattice structures. And so lattice structures can break apart when they are put in water. So in water, an ionic compound will dissociate. Well, what does dissociate mean, and why is it different from dissolving? Dissociate means that it will break apart into its ions. So an ionic compound is the only type of compound that specifically dissociates in water. Covalent compounds will dissolve. Ionic compounds dissociate, because we know that covalent compounds are not made up of ions. So by definition, they cannot dissociate if the definition of dissociation is to break apart into ions. So if we take a look at this example here, we have some solid sodium chloride. And if we put that in water, it doesn't just become sodium chloride aqueous. It breaks apart into sodium plus and chloride minus, and those are both aqueous. So again, if we look at something like carbon dioxide, maybe carbon dioxide is not a good one. Let's look at sugar. If we have C6H12O6 and it's in the solid form, you take it and you put it into water, then we end up with C6H12O6 aqueous. So nothing here has actually changed in the structure of the compound. But for the sodium chloride, it breaks apart. Its structure has actually changed. Okay. So then we can look at strontium nitrate, for example, as well. That's another ionic compound. And so for strontium nitrate, we know that strontium will be strontium 2 plus, nitrate becomes NO3 minus, and we still have to stay balanced. So on the left side, we have 2 nitrates. So on the right side, we have to have 2 nitrates as well. So when we're dissociating or when we're breaking down, we have to keep it balanced. Okay. Now, one other thing that I want to point out is anything that dissociates in water is called an electrolyte. An electrolyte is anything that dissociates in water. So by definition, ionic compounds are electrolytes. Ionic compounds are electrolytes. Covalent compounds are called non-electrolytes because they do not dissociate. So they are called non-electrolytes, all one word. Now, you might also hear the terminology of a strong electrolyte versus a weak electrolyte. A strong electrolyte just means that it completely dissociates. So we don't have any solid NaCl left over. A weak electrolyte would mean that we still have some of the solid left and some aqueous. So it goes back and forth between the ion forms and the compound form. And we're going to look at that in chapter 10. So for right now, in chapter 9, any ionic compound is considered a strong electrolyte, and any covalent compound is considered a non-electrolyte. So now that we've looked at breaking apart compounds in our water, We understand the idea of dissociation versus dissolving, or dissolution is the fancy term for it. We can understand how much substance, how much solute do we expect to dissolve or dissociate in water. And that is called saturation. And so we're going to look at the definition for what it means to be saturated first. Saturation means that the maximum amount of solute has been dissolved in the solvent. And that's it. We have added as much possible solute, which means that after that point, if you add any more solute, it will not dissolve. It will just sit on the bottom of your beaker or your flask, whatever you're using, and it will not go into the solution. So just to give you an example, this is a number that I'm making up, so I don't think it's exact, but I just want to tell you a little bit about what this saturation limit looks like. For saturation of sodium chloride, for example, you might see something like sodium chloride has a saturation level of 35 grams per 100 milliliters. So what does that mean? And that would be at a specific temperature as well, before I forget to mention that. So maybe that's at 25 degrees Celsius. What that means is that 100 milliliters can only dissolve 35 grams of sodium chloride maximum. If you add 35.5 grams, 0.5 grams will not dissolve, and it will just sit at the bottom of your beaker. However, we talked about if we raise the temperature, that number will increase. So maybe at 30 degrees Celsius, the saturation limit is 40 grams per 100 milliliters of water. So an unsaturated system just means that we are below the maximum amount of solute. So again, keeping with our example of sodium chloride, we could say it is anything less than 35 grams in 100 milliliters at 25 degrees Celsius. But it is possible for us to go past that saturated limit, and that is called a supersaturated solution. So here we actually have more than the max amount of our solute. So again, keeping with our example, that would be anything more than 35 grams in 100 milliliters of water. And you're probably thinking, well, you just said that nothing above 35 grams would dissolve. So how is it possible for us to get a supersaturated solution? We're actually going to look at this in lab, but what you would do is heat up a solution, because we know that at higher temperatures, more solute will dissolve. So you heat up the solution, you add more solute, let it dissolve, and then you slowly bring that temperature back down to 25 degrees or whatever temperature you're dealing with, and now you have more than the 35 grams. But as soon as you add in one more little crystal of sodium chloride, any of that extra, that more than 35 grams, is going to, what we say, crash out of solution. It's going to turn back into a solid. And like I said, we're going to see that in lab. But if you want, you can look up videos of supersaturated solutions. They're very common and pretty cool to look at. So now that we can determine, first of all, if something will dissociate or if it will dissolve, we can look at a solution and determine if it's saturated or not. How can we express how much solute we have in a given solvent? We look at the concentration. So the definition of a concentration is the amount of solute in a solution. And there are lots of different ways for us to express that concentration. The first one here is called a mass to mass percent. And that's exactly what it sounds like. It's the mass in grams of the solute over the mass in grams of the entire solution. So you would just take whatever mass of the solute you're using, so maybe 20 grams of sodium chloride, over the mass of your total solution, maybe that's 105 grams, and then multiply that by 100. You can do the exact same thing, but with volumes, and that's called the volume percent. And actually, before we move on, I should point out that sometimes the mass percent is written as the weight percent, because mass and weight are essentially the same thing. And so you might see it abbreviated as WW percent or abbreviated as MM percent. Either one of those is valid. So for volume percent, you might just see VV percent. And here we take our milliliters of solute over milliliters of the entire solution. So here, it's more likely that we're dealing with an aqueous or a liquid solvent. So for instance, if we're adding vinegar to water, we would measure the volume percent much more likely than we would measure the mass percent. Then we have something called the mass to volume percent. And so here we take our grams of solute over our milliliters of the entire solution. So again, this could either be expressed as M to V percent or WV percent. And so for those of you who are going to be in healthcare, most of the time when you're making solutions, especially for like IVs and things of that nature, it's likely that you'll be dealing with these three different types of expressing concentration. So I want you to be familiar with seeing it as an M or a W, of these kind of simplified ways of looking at it. So again, here it's grams per milliliter times 100. This is one that you'll see probably most often, the mass to volume percent, in your careers. So I wanted to try out an example problem with this. And it's relatively straightforward. So we're told we have 25 grams of potassium chloride dissolved in enough water to make 25 milliliters of a solution. Find the weight to volume percent. So we say, okay, potassium chloride versus water. The potassium chloride is my solute. The water is my solvent. And we're told we have 25 grams of our solute. So that goes here. We have 250 milliliters of our solution. So that goes here. Divide those, multiply by 100, and we see that it's a 10% solution of KCl. Now again, since mass to volume percent is so common, sometimes people won't even write that it's a WV percentage. It's just kind of expected to be known because it's so common. So let's look at some other ways that we can express concentration, because there's lots. Our next two are called parts per million and parts per billion. So parts per million we usually abbreviate as ppm, and parts per billion we usually abbreviate as ppb. And you'll notice that these two equations look almost identical. The only difference is that in parts per million, we multiply by 1,000,000, and in parts per billion, we multiply by 1,000,000,000. Pretty straightforward again. Just make sure that you're in grams of your solute and milliliters of your solution. Now these are more specifically for very, very small concentrations. So you're likely to see something with ppm or ppb in topics that are used by the EPA, the Environmental Protection Agency, for example, when looking at how much lead or how much mercury we can have in our water, things like that. It's also common for the FDA when they're figuring out how much of a certain substance can be in our food. So it's likely, or it's possible, that you will see these but it is more common that you'll see these in actual more chemistry terms than in healthcare. So again, for small amounts, we like to use ppm and ppb. And then the next one that we're going to look at is the most common way that we express concentration in chemistry, and that is molarity. Molarity is moles of solute over liters of solution. So this is the only one that we've looked at that has moles instead of just grams. And we abbreviate molarity with a capital M. So you've probably seen in lab, in some of the procedures, you saw something like 0.5 M solution. That M stood for molarity. And the way we would say it is a 0.5 molar solution, for example. So it says here, if we have, again, 25 grams of potassium chloride dissolved in enough water to make 250 milliliters of a solution, let's find the molarity. So what we would do first is convert our grams into moles. And we know how to do that. We looked at that in chapter 6. So from your periodic table, you would find the molar mass of the potassium chloride, which we find is 74. Divide those two, and we get 0.34 moles of potassium chloride. Once we have our moles, we can divide by our volume, but our volume right now is in milliliters, and we need it to be in liters. So remember, to move from milliliters to liters, you have two options. You can do the long way, which is setting up the dimensional analysis. So we would put milliliters on the bottom, liters on the top. There's 1,000 milliliters in 1 liter. You could do it that way, or we could just move this decimal over 3 spaces to the right. Sorry, that's the left. 3 spaces to the left. So we end up with 0.25 liters. So we take our moles divided by our liters, and that gives us our molarity. So we would say that this is a 1.35 molar solution of potassium chloride. Again, this is the most common expression of concentration in chemistry. So if we were actually in the lab together, 99% of what we would work with would be different molarity solutions, not so much the weight to volume. But again, weight to volume is much more common in biology courses. So you probably have or will see one of the two. Now, one other type of expression that we're going to look at for concentration is called an equivalence. And equivalents are most popular or most common in healthcare because a lot of the time there might be some kind of an imbalance with our ions in our bodies. And so we need to make sure that we are putting into our body in an IV, for instance, the correct amount of a given ion to help bring back an equilibrium to the person's body. So what is an equivalent? It is based on the charge of a solute. So the charge determines the number of moles that are in an equivalent. And so we abbreviate equivalent as capital E lowercase q. So for instance, if we looked at sodium, sodium has a +1 charge. So that means that there's 1 equivalent of sodium. So 1 mole equals 1 equivalent. It's a 1-to-1 ratio. So 2 moles would equal 2 equivalents, and so on. But if we look at calcium, calcium has a 2+ charge. So it's a 1-to-2 ratio, because we have 1 mole of calcium to 2 of our charge. So it's 1 mole to 2 equivalents. 1-to-2 ratio means that then if we had 2 moles of calcium, we would have 4 equivalents of calcium. Okay. Now, it doesn't matter if your ion is positively charged or negatively charged. That is arbitrary. It doesn't matter. You're just looking at the value. Is it 1, 2, 3, 4, etc.? That's what we're looking for. So let's take a look at this problem where we want to know what is the equivalence per liter. So most of the time you'll see an equivalence associated with a volume. What is the equivalence per liter concentration of phosphate in a solution that was prepared by making 250 milliliters of a solution with 120 grams of aluminum phosphate? Now, I didn't have enough room on this particular slide, so I moved over to a blank one. So as always, you can see this is a rather lengthy question, but we always start with what is given to us. And we're given the grams of aluminum phosphate. And like with every stoichiometry problem, we have to go step by step. So our first step here, since we don't have a balanced chemical equation, we don't have any chemical equation, is to go straight into changing our grams into moles. So again, we figure out the molar mass of aluminum phosphate, and we are able then to cancel out our gram values, and now we're in moles. Then we do our mole to mole ratio. Again, for this particular problem, we don't have a balanced chemical equation, so our mole ratio is the intermole ratio, the IMR that we looked at in chapter 6. The intermole ratio for phosphate versus the entire compound is a 1-to-1 ratio. There is one phosphate ion in every one compound of aluminum phosphate. So that way we cancel out our aluminum phosphate. And then we know that our next step in a stoichiometry problem is to convert out of moles and into whatever unit the question asks for. So this question asks for equivalence. So as we just saw before, we need to pay attention to the charge. So here the charge is 3. Again, the negative doesn't matter. So that means that for every 1 mole of phosphate, we have 3 equivalents of phosphate. So our moles of phosphate cancel out, and after we go through and do our math, we end up with 2.95 equivalents left. But again, the question asked specifically for equivalents per liter. So again, we converted that 250 milliliters into liters, which would give us 0.25. And so we take our equivalents, we divide by our liters, and we get 11.8 equivalents per liter as our final answer. So again, we're just dealing with stoichiometry. Use those same steps that we looked at in chapter 6. Step 1, if necessary, balance the chemical equation. We didn't have a chemical equation here, so we could ignore that step. Step 2, convert your given unit into moles. We were in grams, so to get to moles, we use the molar mass. Step 3 is to convert from your given substance into your wanted substance using a mole-to-mole ratio. And that mole ratio can either be from the balanced equation, those coefficients, or the intermole ratio. So in this case, it was the intermole ratio. We did that. And then the last step, step 4 of a stoichiometry problem, is to get out of moles and into whatever unit the question asks for. Question asked for equivalence, so we saw that that was a 1-to-3 ratio, and we solved there. All right, so we're just using the topics and the understandings that we looked at in earlier chapters in order to go through and solve these. Now, not every solution is at the correct concentration that you want to be using in your given experiment or in the field. So we have to do something called a dilution. And a dilution just means that we are decreasing the concentration of a solution. And the number one way that we do that is we add more solvent. By adding more solvent, we end up with a smaller concentration. The way that we can determine how much extra water we might need to add or what our new concentration would be after adding water, because again, we're dealing with aqueous solutions, is using this equation, C1V1 equals C2V2, where C equals concentration. So this can be in any concentration unit, but again, for chemistry, 99% of the time, we look at molarity. So that's most often the concentration unit that we will be using. V stands for volume, and it can be in any unit, but most of the time it's in milliliters. So concentration can be in anything, volume can be in anything, but again, most of the time we'll be in molarity and milliliters. So on one side of our equation, we have C1V1. So those are our initial information. And so most of the time, that side of our equation is the concentrated solution. C2V2 is what we are changing the concentration to. So this is usually the dilute side. Now, this doesn't have to be the case. If you put the dilute on the left and the concentrated on the right, you'll end up with the same answer. But just make sure that you're putting the two pieces together on the correct side of your equation. So let's take a look at this problem. If you have a stock solution, and that just means that when you order that compound, that's how it comes. If you have a stock solution of 12.1 molar hydrochloric acid, how could you make 250 milliliters of a 2.5 molar HCl solution instead? So you're in the lab, you want to use 2.5 molar, but you only have 12.1. We need to dilute that down. So we see that C1, our concentrated solution, is 12.1. How do we know it's more concentrated? It's a higher number. So the higher the molarity, the more concentrated it is. V1 is what we're looking for. We're trying to figure out how much of that 12.1 molar solution we need in order for it to become a new solution. So our goal concentration is 2.5 molar, and we want our new solution to be 250 milliliters. So once we figure out all of our different variables, we can go ahead and plug them into our equation. And just to make sure that you're feeling comfortable with the algebra, what you would do is multiply these two numbers together first, find out what that answer is, and then just divide both sides by the 12.1, and that would give you V1. So the value we get for V1 is 51.65 milliliters. Well, what the heck does that mean? What are we doing with that 51.65 milliliters? What that means is that you are going to take 51.65 milliliters of the 12.1 molar HCl. You're going to pour that out, and then you're going to add water until you reach a total of 250 milliliters. And now your solution is 2.5 molar instead of 12.1. So this was just telling us how much of our concentrated did we need to start with and then add water to in order to make our new solution. So let's take a look at this second one. If you add 50 milliliters of water to a 150 milliliter solution of 2.5 molar sodium chloride, what would be the molarity of the final solution or the new solution? So here, our initial concentration is 2.5 molar, and we're told that we have 150 milliliters of that solution. So those are my C1 and my V1. We're looking for the new molarity, so we're looking for C2. And V2 here, a lot of the time people are tempted to just put 50, but we're adding 50 milliliters to a solution that's already 150 milliliters. So our V2 is now those two volumes put together, which is 200 milliliters. So we plug in. Again, we just algebraically solve for C2, and we end up with a concentration of 1.88 molar. Now, one thing that I do want to point out is you can usually kind of guess if you're on the right track. So for instance, we know that we're diluting 2.5 molar. So if you get an answer that's larger than 2.5, you know that you made an error somewhere, either in your math or your setup. So if you were to just use 50 as your V2 instead of 50 plus 150, you would get a number bigger than 2.5, and you would go, oh wait, something isn't correct here. So always kind of look out for things like that. Even when you're taking the test, if you see an answer choice that is greater than 2.5, you know that you can automatically cross that one out, that cannot be the answer. Okay? So the remainder of Chapter 9 is going to look at some different properties that solutions have. We'll do that together in class, and then we will look specifically at solutions that contain acids and base.